cutting up cheese is something we do nearly every day. Now, suppose that this cheese is spherical and I want to cut it halfway between here and here, about there. What volume would I remove? Well, by the end of the programme, you should be able to calculate it. You may also be familiar with formulas for the volumes of spheres, cylinders and cones. Even if you don't know them now, we'll show you how to get them during the programme. But we'll begin with the one for a sphere. Now, volumes are no more difficult to calculate than areas, and it'll involve integration. But we need to know what integral to set up. So let's recap on how we found areas. In particular, the area of this quarter circle. Remember, our basic building block is a rectangle because we know its area. We found an underestimate of this quarter circle using these rectangles. This distance is xi, and the radius of the circle is 1, so by Pythagoras' theorem, the height of this rectangle is the square root of 1 minus xi squared. We're going to use delta xi for the width, so the area of the rectangle is this. Its height times its width. Next, we sum over all rectangles from 0 to 1, and taking the limit, as the widths of the rectangles tend to 0, gives us this integral, which we found last time to be pi over 4. So to summarise, we set up an integral by first taking an approximation for the area using rectangles. Then we form the sum, and finally we take the limit as the widths of the rectangles tend to 0, which gives the integral. Now we're going to use exactly the same idea for volumes.
Let's begin by looking at a hemisphere of radius 1. We'll use this process of approximation, sum, then integral, to find its volume. The first step is to approximate the volume, and in this case we'll use discs. These discs are analogous to rectangles for finding areas, and they give an approximation to the volume. Let's take the model apart so that we can see that. Now we can see the discs, and these outer edges, we should note, are at distance 1 from the centre of the hemisphere. We'll need that in a minute. Let's concentrate on this disc. Now I've got that disc on another model here. Now you'll remember that this is an outer edge, and so is at distance 1 from the centre, and so this distance is 1. This distance is xi, and so by Pythagoras' theorem, this distance is the square root of 1 minus xi squared. Now the thickness of the disc is delta xi, so its volume is pi times radius squared times thickness, and I've written this down over here. It's pi times radius squared, that's 1 minus xi squared, times thickness, delta xi. And adding up the volumes of all the discs from 0 to 1 gives this sum. And taking the limit as the thickness delta xi tends to 0 gives this expression for the volume of the hemisphere. And I can write that as this integral. Now that's the hard work done, because now we've got an integral and we know how to evaluate this. Pi is a constant. 1 has primitive x, and a primitive of minus x squared is minus x cubed over 3. and I need to evaluate that expression from x equals 0 to x equals 1. And if I do so, I get 2 pi by 3. So the volume of a hemisphere of radius 1 is 2 pi by 3, and so the volume of a sphere of radius 1 is 4 pi by 3. We'll come back to the general situation of a sphere of radius r later.
I said at the beginning that we would find formulas for the volumes of spheres and cylinders. But Dave has just assumed that the volume of this cylinder was pi times the radius squared times the thickness. Now that's the area of this circle times the thickness. We need to justify that. When we were finding areas, we used rectangles to get our approximation, because we knew the area of a rectangle. Now we'll approximate volumes using blocks, because we know the volume of a block. It's height times width times thickness. Now this model shows how we're going to approximate the volume of a cylinder, and because of symmetry we only need to look at this quarter. We've approximated the volume with blocks, like this one. So here's an approximation for the volume of a quarter cylinder of radius r. That's the approximation. The next step is to write down the sum. We'll need to find the volume of the blocks. We've seen a diagram similar to this already. The length along the x-axis is xi. The hypotenuse, the radius of the cylinder, is r. So the height of this block is, by Pythagoras' theorem, the square root of r squared minus xi squared. Now, the width of a block is delta xi, and its thickness is h. Let's write that down. For the volume of the block, then, its height is the square root of r squared minus xi squared, times its width, that's delta xi, multiplied by its thickness, that's h. So, summing over all blocks from 0 to r gives this. Now, we can take h out in front of the sum to give h multiplied by this sum. Now look at this sum. Each term is the height times the width. So each term gives the area of a rectangle. So the sum corresponds to the area of all the rectangles, and so approximates the area of the quarter circle. So this whole expression for the volume of a quarter cylinder is h times the area of a quarter circle. And that's h multiplied by pi r squared over 4, or pi r squared h. So the volume of a whole cylinder V is pi r squared h.
We'll use the same method of approximation to find the volume of this pyramid. It's got height h, and its base is a square, whose side has length b. What we have to do first is to decide how to approximate the volume. And I'll approximate it like this. This time, each block has square cross-section. We need an expression for the volume of this block. If it's xi from the vertex, and we call the height yi, then the square has side twice that, and so its area is 4yi squared. So the volume is area 4yi squared times thickness, delta xi. And I've written that down here. So to get the volume of the pyramid, we sum over all blocks from 0 to h and take the limit as delta xi tends to 0. Now to make progress, I need to rewrite this yi squared in terms of xi's. Well, here we can see the angle theta, which is half the angle at the top of the pyramid. And tan theta is just yi divided by xi. In other words, yi equals xi tan theta. Making this substitution gives this. And we can write this expression as this integral. Now, we can evaluate that integral, and as before, 4 tan squared theta is just a constant, and x squared has primitive 1/3 x cubed. Evaluating this from x equals 0 to x equals h gives this expression as the volume of the pyramid. Now this formula is probably not the one that you're familiar with. We need to express it in terms of the height h of the pyramid and its base b. But here we can see that tan theta equals b over 2 divided by h, or 2h tan theta equals b. Making this substitution, we can rewrite this last expression as 1/3 b squared h. And you may recognise that as 1/3 base area times height.
Now let's look at this similar volume. It's a cone. Out of this, we'll find a general method which will work for nearly all the volumes you'll ever need to find. So we're going to find the volume of this cone, which is circular base of radius r and height h. I'll approximate it this way, using discs. This disc is xi from the vertex, and its radius is yi. So if we write down its volume, it's the area times the thickness. That's pi yi squared times delta x I. So summing over all discs from 0 to h, we have this. Now, taking the limit as delta xi tends to 0 gives an integral which we can write as the integral from 0 to h of pi y squared dx. If you look at this integral for the volume, the surprising thing is that we haven't used the fact that we're dealing with a cone. Now that will come in when we write this y squared in terms of something involving x. All that we've used so far is the fact that the cone has circular cross-section. Now one way of getting volumes with circular cross-section is to take the area under a curve and rotate it about the x-axis. A volume like this is called a volume of revolution. It has circular cross-section, so we can approximate its volume using discs. And the formula we just obtained for the cone works for all volumes of revolution. The formula for the volume is the same. It's pi y squared dx, as before, but now with the appropriate limits of integration from a to b. To use this formula, I have to do two things. First, I have to put in the appropriate limits of integration, and second, I have to put in what y is in terms of x. So let's do that for the cone. First, the correct limits are from 0 to the height of the cone, h. Second, we put y in terms of x. Now we can see that y is equal to x tan theta. And so the volume is the integral from 0 to h of pi x squared tan squared theta dx. Now, as before, pi tan squared x is a constant. Sorry, pi tan squared theta is a constant. And x cubed over 3 is a primitive of x squared. And that's from 0 to h. Evaluating this gives pi h cubed tan squared theta all over 3. Again, we can express this in terms of the base dimension, because here r is equal to h tan theta. And so we get the volume of 1/3 pi r squared h. And it's 1/3 the base area times the height, which, you remember, is the same as we got for the pyramid.
Let's return now to our sphere of radius r. Firstly, we can see that a sphere is a volume of revolution. The area between this semicircle and the x-axis, when rotated, generates a sphere. Here's the formula for the volume. We need to do two things. First, get the limits. They are minus r and r. Second, we need to get a formula for y. Let's look at this point with coordinates x, y. Now, this distance is x, and this radius is the radius of the sphere. And so, by Pythagoras' theorem, y must be equal to the square root of r squared minus x squared. Substituting r squared minus x squared for y squared gives this integral. And we can evaluate that. Pi is a constant. A primitive of r squared is just r squared x. A primitive of minus x squared is minus x cubed over 3, and we must evaluate that from x equals minus r to r. And if I do so, I get 4/3 pi r cubed for the volume of a sphere.
Finally, let's go back to our cheese problem. Remember that we're assuming it's a sphere, and we're going to cut the cheese here. That's halfway between the centre line and the edge, at r/2. What volume of cheese will I cut off? Well, we can find out by rotating just this bit of the semicircle round the x-axis rather than the whole semicircle. So all we need to do is to alter the limits of integration in the integral that Dave has just evaluated. The limits of integration we need here are from r/2 to r. So I'll put them in here and here. We'll leave you to do the evaluation, but the answer is 5/24 of pi r cubed. You may be surprised at how small a proportion of the whole cheese this is. But the important thing for you to remember is that a volume of revolution is given by this integral. That's the integral of pi y squared dx with the appropriate limits of integration.